the artificial intelligence revolution is accelerating toward a hard physical limit, the thermal wall. Next-generation high-wattage logic chips are running so hot they are physically unable to function, forcing them to throttle performance and shut down. To cool these processors, the industry relies on 19th-century mechanics. We surround advanced silicon with massive arrays of fans, complex liquid manifolds, and chilled water loops. This creates the cooling tax. Data centers are wasting a huge percentage of their total grid power on overhead, expending massive amounts of energy simply to keep the hardware from critical thermal failure. By trying to outbuild the heat with more plumbing, the industry is creating a fragile, inefficient, and expensive liability that threatens the growth of AI itself. We measure this inefficiency using power usage effectiveness, or PUE. The industry average of 1.58 means that for every watt powering the actual servers, more than half a watt is burned entirely on facility overhead. This reliance on thermodynamic plumbing drains local ecosystems. Evaporative cooling systems burn through billions of gallons of fresh water annually, worsening the regional water scarcity seen here at Lake Mead. The economic fallout hits surrounding communities just as hard. The inefficient power draw of these cooling systems strains national grids, triggering power price spikes, reaching over 267% for local residents in data center hubs. Legacy data centers are parasitizing local resources and economies. Resolving this requires a shift in physics, not an incremental hardware upgrade. The solution to the thermal wall doesn't require deeper resource extraction or more water. The industry must move from macro plumbing to atomic engineering at the chip interface.
The CAIDI Institute has engineered the HiGTP 200 protocol. It is a solid-state, passive thermal superconductor designed to replace failure-prone mechanical cooling. Current industry standards rely on heavy copper heat spreaders. Under extreme loads, copper acts as a thermal choke point, trapping energy directly above the die. By utilizing an aligned turbostratic graphene lattice, the HiG protocol achieves ballistic lateral transport, wicking extreme heat sideways significantly faster. Removing the copper choke point at the atomic level eliminates the root cause of the heat backup. It renders massive, facility-level plumbing obsolete. The material's structure relies on vertical nanosprings, copper nanowires aligned into direct thermal pathways. Under physical pressure, these springs act as a compressible gasket. They compress to guarantee 100% surface contact with the silicon die, eliminating the microscopic air gaps that trap heat. This architecture achieves a thermal conductivity exceeding 1,500 watts per meter Kelvin, nearly 4 times the efficiency of legacy copper, without a single moving part. This atomic-scale engineering dismantles the thermal wall. It replaces the complex, failing network of facility plumbing with a single, solid-state interface. When this solid-state cure is applied to hyperscale infrastructure, using Amazon's 1,000-gigawatt footprint as a baseline, the financial stakes are immense. This chart shows the financial and environmental performance of top operators. Eliminating the cooling tax drastically cuts expenditure. Looking at the 40% revenue growth metric, operators reclaim billions in lost compute revenue, while the lightweight graphene material extends hardware lifespan. This economic inversion rewrites the profitability of AI hardware, turning a massive operational liability into recovered revenue. For operators investing in clean energy like nuclear reactors, the HYG material ensures every kilowatt generated is utilized for compute, compressing the PUE down toward a theoretical physical limit of 1.08. Because the material wicks heat so efficiently, liquid loops can operate at higher inlet temperatures. This enables a total transition to dry cooling radiators that consume zero water, preserving regional water tables and fulfilling water stewardship commitments years ahead of schedule. Stripping out the cooling overhead creates the powerful negawatt effect. By returning gigawatts of unused capacity to the utility grid, data centers act as a stabilizing force, shielding local communities from brownouts and price gouging. Stop managing thermodynamic liabilities with outdated plumbing grifts. Invest in the solid-state cure. The CAIDI Institute builds the physical infrastructure of the next energy era.